Welcome back. Today we're going to talk about BGP. BGP is going to be the only exterior gateway protocol, and it is considered a path vector protocol. As we mentioned during the OSPF session, an IGP protocol, we're going to see that commonly within an organization, versus BGP is going to help communicate different organizations. It is considered a path vector protocol because it considers the entire path and is going to think and account for the whole organization, the whole bubble that is going to see, versus a distance vector, for example, like RIP, that again only cares about how far that destination is. BGP, it is the only protocol on the internet really that will help. That is how the internet communicates between organizations, between ISPs. It is very, very scalable, but that comes with a price, and BGP is just slightly slower than an IGP. And this is how BGP is going to represent, or how it's going to think about each path for a destination. BGP cares about the autonomous system, and again, that's going to be just a big cloud, a big bubble, and it doesn't necessarily care of how things move within it, but it's going to provide a metric, it's going to provide a rating for that particular bubble, and every single organization across our path will have its own rating, its own metric, and that's how it's going to determine the best path for a particular destination. So in this example, very simplistic, this is kind of what we see on the internet. It's just a bunch of different organizations talking to each other. And in this particular example, we are on the top corner over there. So if we want to go to the web server in Autonomous System 1024, we have different ways to do that. Maybe we want to go just straight at the top level with all those balls, or maybe we need to bounce between all of them like in a zigzag until we get to that particular web server. Again, BGP is going to create a path, and is going to create assign like a metric for each particular organization, and that's how it's going to calculate which path is better for our destination. The autonomous system numbers, and just remember this for the exam, we have publicly assigned numbers that we are going to see in the real world on the internet. There's the original range. It was only 2 bytes from 1 to 65,535. Then that was expanded using 4 bytes, as you can see on the screen. I don't want to try to pronounce that huge number. But those again are going to be real numbers, real organizations that when we connect to the internet and when we see the path on our routing table. The private autonomous system is something that we can use on our labs, internally, within our organization, for ease of communication, because those numbers, we can randomly pick them, but the one publicly assigned, again, they were assigned by different organizations, and those are the ones that ISPs or other organizations will expect to see when we communicate with them. The BGP basics, it runs on TCP port 179. It's not like OSPF, that's its own protocol. It is classified as a path vector, like we mentioned before. It's going to form neighborship with its peers, similar to OSPF. Different requirements, obviously, but it's going to create similar communication between the neighbors. And is going to advertise prefixes and the path attributes. That's how there are all those different values that come together with our prefixes are the path attributes. eBGP versus IBGP is how BGP is going to behave slightly different depending on who are we pairing with. If we are pairing with another router within our same autonomous system, is going to be an internal IBGP connection. If we are pairing with someone else, a different organization, meaning a different autonomous system, is going to be considered eBGP or an external BGP connection. And that is going to just indicate BGP what's going on and how it should behave if it is something own or something that we recognize within our organization or an external one. The BGP messages that we're going to see is open. It's going to be the first message when we're trying to establish that neighborship, when we're trying to communicate with the other peer. Once the neighborship is established, we're going to also see keep alive just to maintain that peering. The update messages is where the actual information is going to be sent, all the prefixes and the attributes. And the notification messages are going to signal some type of error or some type of change that we need to make our peer aware. The routing information basis is the logic process of how BGP is going to operate, how it's going to receive the route, what's going to happen after that, how it's going to calculate which one is the best, and eventually how that gets dumped into the routing table. Fortinet has a really good article on how that interaction between the routing information happens. So I'll show you that when we go to the lab. But it is really good to understand the different steps, especially when filtering happens for the BGP operation. The different BGP attributes that we're going to see on the routes is going to be the AS path. This is going to be a collection of all the different autonomous systems that we have to reach in order to get the particular destination that is being advertised. The local preference, as the name stands, is going to be a local internal to the autonomous system to try to prioritize a route over another one. This information is not shared on an eBGP connection. It is shared between IBGPs. The next hub is just the next where we need to send the traffic when we're trying to reach that particular destination. The multi-exit discriminator, or MED, for sure is just an external path preference. And the community is going to be additional tags that we can add to our prefixes. The BGP route selection is going to follow these criteria to determine what is the best path for a particular destination. The local preference will be the first choice, and remember, the local preference only significant for that particular autonomous system. Then the shortest AS path, and we're going to see that on the lab. The origin is the preference given to how that particular route was added to BGP. The BGP come from different sources. Maybe it was redistributed from a different routing process like OSPF or a static route. Maybe it was statically assigned when we were configuring BGP, or maybe it is unknown. And unknown is just usually redistributions that are coming from second redistribution, I should say. Something maybe OSPF had a autonomous system border router that is sending some information, and then OSPF is injecting that into BGP. That is where it become unknown because we don't know the true source. Things like that. That is also going to have some weight. The MED, and finally, how old that route has been on the routing table. The oldest, the better, because it considers how stable that route was. It's been stable. We learned that so many X amount of time ago. We are going to prefer that. Again, I'm going to show you a different article on that when we go to the lab that explains that a little bit more details and show us how we can learn that to remember. I mean, how can we can remember that for the test. Configure BGP. This is just a snippet of how we will do that on the CLI. The important thing here to know is that when we configure the BGP process, we need to define which is going to be our autonomous system. And every time we configure a neighbor, yes, we need the IP of that neighbor, but we need to know, we need to tell our BGP process that neighbor belongs to X autonomous system. And with that information, it's going to try to match the autonomous system that we configured earlier for our process. If it is the same, then the router knows, well, that's an internal BGP connection. If it is different, well, that's an eBGP connection, and behave differently according to that. One thing that we didn't mention before is that all iBGP routers within our autonomous system must have a connection to all other routers. And that is going to get tricky the bigger our environment is, the more routers we have, those connections are going to increase exponentially. So the route reflectors comes into play to save the day to reduce the number of iBGP connections that we need in our environment. Instead of connecting all routers to all routers and have an exponential number of connections every time we add one of them, we can connect to a single point. We can have multiples in our environment depending on the size, but we can go and connect to the route reflector, and the route reflector is just going to share everything it learns. It's kind of similar to the role of a designated router in OSPF, in the sense that it's receiving all the information from the other routers, and then it is redistributing that across the network. Similar concept, but it will accomplish that all routers within our iBGP, within our autonomous system, are able to know the information from all other routers. So it will be something like this. If we have iBGP requires a full mesh. So in this particular example, we have 5 routers. We have all those connections all over the place. As soon as we add one extra, right, a 6th router, then each single router, instead of you only have 4 connections, now we have 5. Going to all routers is just going to get very complicated and resource intensive. Versus if we have a route reflector, we can have all the other routers connect to a central point, and from that, the information gets redistributed to everybody else. Like any other routing protocol, we can redistribute routes from different sources, static, RIP, OSPF, into our BGP process. When it comes to filtering, we have many options. We can use an access list, a prefix list, a route map, or all the above. An access list is going to be very easy and very simple actions. It's going to be either a deny or a permit, and it's just going to be very limited on how we can use it. But again, it's going to be very simple to use at the same time. And this is just an example of how we configure that access list and how we can apply that into our BGP process. A prefix list is going to be very similar, but it's going to give us a little bit more flexibility than an access list. With a prefix list, it's going to be similar concept. We're going to define a prefix. We're going to set an action, but we can also have some variability in the sense of this example. We are setting the set greater or equal than 16. So instead of us creating 8 different rules to allow 10.00/8, 10.00/9/10/11, the prefix list is just going to give us that flexibility. Just with one command, we're taking the range from 8 to/16, we're going to allow that. And then we can very easily assign that and use that in our BGP process. The route map is where the Pandora box gets open. Really, we can use the route map is going to be way more flexible on how we can use it, how we can apply the rules, and the best part is that we can combine prefix lists or access lists within a route map. So we can define, hey, these are going to be the prefixes or the accesses I want to use, apply this set of rules to those prefixes. So then the power of the route map comes when we start combining access lists and prefix lists into it, and the flexibility with all the options the route map can offer us is just going to enable us to be more precise with the tuning and notifications that we want to do when we use the route map. The network import check, it is enabled by default on BGP, and what it's going to do, it is going to prevent for us to advertise a route, a prefix on our BGP process if we don't have that prefix already on our routing table. So for example, when we were doing the OSPF section, we did a lazy way of define a subnet. We did 10.0.0/8, and that is going to account for everything, all those interfaces, all those subnets within within that range, and it's going to advertise those particular ranges. BGP is not going to do that kind of like inspection, let's say, to look like, oh, I have this range, let's see what's inside of it. It's just going to try to advertise that particular range, and if that doesn't exist in a routing table first, either by OSPF, maybe statics, or connected for any other source, it won't advertise that. And we're going to demonstrate that on the lab as well. But just keep in mind that the set import check is enabled by default. Troubleshooting. BGP, similar to OSPF, is going to go through different states when it's establishing that peering, that neighborship with the peer that we define in our BGP process. And these are the different steps that we could see when that is happening. The idle, really nothing is happening. The connect, we move to connect when we send that initial TCP message. We're going to go to the active while that TCP connection is happening. Once that's established, we're going to move to the open set, then open confirm, depending on all the different values and settings that we're trying to negotiate with our peer. And finally, once the exchange of the update message has happened, meaning both ways, I already share my information, you share your information, we already processed that, we're going to go into the established state. This is just a snippet of how the get router info BGP neighbor is going to look. Really, we care about what's the IP of that neighbor, what's the remote AS, what's our local, because that will easily tell us, hey, this is a eBGP or iBGP connection, what type of BGP version we are running for IPv4 or BGP6 for IPv6, if it is established, how long since then, things like that. The BGP summary command will give us a quick overview of the state of our different peers, and we are going to see that on the lab in more detail. Here just we have a little description of what each value represents for the previous command. The one I want to stop for a little bit is the last one, the state/prefix. That is going to show us the state of the BGP neighborship if it is any other than established. When it comes to established, it immediately turns into a number, which will tell us how many prefixes we have received from our peer. If we see something else, if we see letters, active, idle, open, connect, something like that, we know the process is either the BGP peering is either getting established or is stuck in some way. If we see a number, we know the BGP peering has been established and we are receiving that many routes from our peer. Clearing the BGP connection, we can easily do that with the execute router clear BGP all. That is obviously going to remove everything we have learned from our peer. The peering will have to get reestablished unless we enable the soft command and we configure our peer for that, which I will show you that in the lab. But if we do the soft, what it's doing is just without removing the routes and without removing the peering, it's just trying to going to soft reset that connection to try to exchange and force the update messages to happen because BGP is just a little bit slower, as we mentioned before. The advertisement interval for BGP is 30 seconds on a FortiGate firewall. So once we get something, the router receives a route, it's going to wait 30 seconds before it advertises that to their other BGP peers. Here we have a few important commands when it comes to debugging. BGP all enable, diagnose IP route, BGP all enable, or maybe the level info, and how we can do some filtering knowing that BGP runs on TCP port 179 that could help us to filter the information that we are seeing. Finally, let's go to the lab. Let's review the articles I mentioned before, and let's get our hands dirty with BGP configuration. All right, so these are the articles I wanted to show you. The first one is the route map. It's just go through what a route map is, all the different options that we have. But really, I just want you guys to pay attention to the flexibility that we get from a route map, which is going to give us that flexibility and that power that we want on our BGP configuration. All the different actions, all the different things that we can set, meaning that we can configure. Oopsie, I said it wrong. We'll start over. So this is the first article I wanted to show you. This is just going to go through what a route map is, how we can configure it, and all the different options that we have. But really, I just want you to point out all the different things that we can match when we're doing a route map, using a route map, which is going to give us the flexibility and the power of it. So we can match on all these different values. So once we have identified our prefix in any of these ways, then we can set all these different actions, right? We can, no, that wasn't the set, correct? Yeah, that was the one. We can set all these different actions on, apply those actions to our configurations once we already identify what we were looking. So we're matching on many different elements. We can do the IP address or maybe the AS path, and then we can apply all these other settings. So just go over that article, pretty good on that. The second one is this, the route selection process. One that we didn't mention on this slide is the wait. Just because this is a local significant value for each firewall and each router on our BGP environment. But then just try to memorize all the different steps the firewall is going to go through to determine which one is the best BGP path. The next article just talked about the routing information basis, how it's going to operate once we receive an update message it goes to the RIP in. We can apply some rules to that before it goes to the local RIP, which eventually is going to dump that into a routing table. And then from the routing table, when our firewall is actually sending update messages, is going to go through the policy first before it goes to the RIP out, and then eventually to our peer on an update message. So that was pretty good too. And lastly, we have this article. It just talks about how we can leverage loopback addresses, and that is the recommended way of configuring BGP. So we can abstract the underlying technology, I should say infrastructure. So we can abstract the underlying infrastructure for BGP peerings. But there's 3 considerations for that, and that's what we're going to do in our lab. We're going to use loopback addresses that are already pre-configured. So our environment is going to look like this. It's the same one we've been working for the past few lessons. Branch A on the left, HQ on the middle, and then we have branch B on the right. I configure the particular loopback address for each one of them, 1.177 and 2.2 for each particular router. And again, when we have loopback addresses, there are 3 considerations that we need to pay attention to. The first one is routing. It is a new interface, it's a new subnet, new IP. We need to make sure our peer is able to route to that address. So I already add our particular loopback addresses to our OSPF process. Second consideration is going to be access, because now in contrary to OSPF, for example, we're in or a different configuration of BGP too, instead of just connecting to our the same interface on the other end of our cable, now we need to traverse that interface in order to reach our virtual interface. So we need an access, allow access for that. For simplicity, I just include that loopback address into my allow all, but usually you just want to have a allow BGP protocol in those interfaces, the loopback and the receiving interface. And the third consideration when you're using loopback addresses is the time to leave. By default, BGP is going to assume that our peer is directly connected to us. So it's just going to, for that TCP message, it's going to set a time to leave of 1. So once that the remote peer receives that, that message is not going further. But because now that message needs to be processed by the receiving interface and then pass along to our loopback interface, we need to change that time to leave value. We can set it to 2, but I also, and that will be enough, but I like to give myself some wiggle room, and there's some routing chains that I'm not accounting for or some migration that I need. So we're going to set that to 5 in our lab. So I already configured HQ and branch B, and we're going to review the configuration in a moment, but let's configure branch A now. The local AS is going to be 1. The router ID is going to be the same as our loopback interface. We're going to set our peer, is 7.7.7. The remote AS is 77, which is going to be an eBGP connection since it doesn't match our local AS number. I'm going to set the loopback interface as my source again, because I want communication between 1.1.1 and 7.7.7. So I need to update that source when the message is going out. And I'm going to enable soft reconfiguration, as we mentioned earlier. If I do a reset, it is better to have the soft reconfiguration there, so I don't need to necessarily lose everything I learned from my peer. Okay, so then under networks, we're going to advertise our target subnet 172.16.4.0. And this subnet already exists in a routing table because it's a local connected subnet, connected route. And because of that, and the import check, which is enabled by default, then this subnet is going to be advertised to our peers. But if we do something crazy like 44, 33, 22, that subnet won't be advertised to our peers because we do not have that in our routing table. So we're going to see that in a moment. So let's click apply. One more thing that we need to do, we need to update the TTL value, the time to live for our peer, because again, we're using the loopback interfaces, and that's a change that needs to happen on the CLI. So let's do config neighbor, and then we edit our neighbor. First, we're going to set the BGP enable. And once we enable that, then we get another command gets unlocked, which is the eBGP multi-hop TTL, and I'm going to set it to 5 just to give me some wiggle room. Setting it to 2 will be also valid for our environment. So let's end that there. So let's see if we can see what's going on with our peering info BGP summary, and is set to active. Come on. Execute ping 77.7. Yep, we can reach that. Oopsie, just taking its sweet time. Execute router, clear BGP all. Let's see if we can try to force it. Idle, active. Yes, come on. We can do it. Two messages have been sent. Let's see, I didn't miss anything. I don't think so. Edit in CLI, yeah, multi-hop. Everything looks good. There we go. Whew, just took a while. I was getting nervous there. There we go. So as you can see, the state now that the neighborship was established, it changed from letters. Oh, I closed it. To a number. And this is saying that we received something from our peer. So let's see what that is with the get router info routing table all command that we've been using all along. And we are receiving one route, and we know this is coming from branch B just by the subnet 192.168.5.2. It is trunking our BGP advertisements. As you can see, is still enabled. It is trunking that because the administrative distance is 20 versus 110 for OSPF. That's why we are preferring BGP to go to the 192.168.5 192.168.5 subnet. If we do a database command, then everything we've been doing in our previous lab, it is here. We have all those static routes. What this one is doing there. Oh, I guess this is a leftover from my testing. I was going to show you that anyways, but I guess I forgot to delete that. But since we're already here, let's see what branch B is receiving. So branch B is configured. I decided to, instead of using the loopback address, just to show you the TTL situation, I'm using the directly connected IPs, but it's going to be a similar logic. So actually, let's go to HQ because the commands there are going to be better. Not better, but just a little bit more information since we have two peers. Router info BGP summary. So both peers are enabled. We have the 1.1.1 that we are receiving two prefixes, and we are receiving one from our other one, 10.5.5.2. If we check what those are, let's get router info, routing table all. We are receiving the 4.3322. Kind of surprise, anticlimactic. And then the 7216 subnet. And because we're using the loopback interfaces, automatically BGP is abstracting the underlying redundancy that we have. And immediately we know that we have two different paths for that destination. And from branch B, we're receiving its subnet 192.168.5. So let's go back to branch A. Let me fix what I did. And here's the subnet that wasn't supposed to be there. And I created just a black hole. And this is just a way for me to represent that particular subnet that I have in our environment. So I can make a match with what I'm telling BGP to advertise. And this is useful when we have like a DMC or we have the need to break our subnet. So imagine we have the need to have multiple DMCs, and really I don't want to necessarily advertise, and sometimes ISPs won't accept anything lower than /24. So instead of me advertising multiple /27, for example, to the ISP, I can create a black hole here that actually match what I'm telling BGP to advertise, and then the other IGPs will handle the traffic to send it to the correct way. So I'm not necessarily killing all connections. But let's assume I didn't forget to remove this from my configuration. And if by removing that in BGP, adding that subnet won't be advertised because it does not exist in my routing table. So if I go here, I get to a database. That 4433 is no longer my database. It's not either on my routing table either. Oh, definitely not there. And now on the BGP, the advertisement probably was removed. There it goes. Because now, although I'm telling my BGP configuration, hey, advertise this subnet, that subnet does not exist in my routing table, therefore BGP won't advertise that. One last command that we can see over here, get router info BGP network, and let's try the 192.168.5.0/24. Oopsie. What happened? Oh, network 192.168.5.0/24. And this is just going to give us the details of that particular network. Who are we advertising that? What was the original AS number that received that information? Where are the different metrics? See the local preference. This is for the autonomous system. It's just set to 100. This particular is the best path. If we go to branch A and we do the same command, just going to copy it, copy, and paste. We're going to see similar information, but notice that the AS path has changed. Whatever's on the right is the oldest. So that particular subnet was originated on AS22. It traversed AS77, and now we received that subnet from our peer 777. As you can see, we are not advertising that to anybody. So it's not, we don't have a peer listed here. But yes, that's BGP in a nutshell. I just wanted to show you the difference of how we can operate it, how it's going to be preferred over OSPF and everything that we built so far, how can monitor and understand the different subnets and routes that we are trying to advertise and at the same time receiving. So one more thing I want to show you, and with the magic of editing, I went and collect some packet capture between HQ branch A and HQ branch B. So this is branch B. Wireshark is listing it as red because the time to live is 1, and usually that is a concern because that packet is just not going to go any further. But we are understanding what BGP is doing. We know this is the default behavior, and because the way I configure HQ and branch B, which are directly connected, I use the directly connected IPs, then we know it is fine. But I just wanted to show you what is kind of the process. Initially, it's going to create, because it runs on port 179, as we can see right here, a TCP, like any other TCP connection, is just going to go through the 3-win handshake. So SYN, SYN ACK, ACK. Once that happens, we're going to send the open message. We were going to send whatever information there. As you can see here was my router ID and some other values. We're going to receive an open message from our peer, some keep alive messages. Eventually, we're going to get this update message, and again, the update message from the other end. So once again, path attributes, what's the information, right, for those. So we are telling, hey, this particular path I learned it from an IGP. The AS path is going to be 22. This is the next hop, which happens to be that router. And over here, we're telling, hey, this is the subnet, right? So I just wanted to show you what's the information, how that BGP peering is going to get established. If we switch to the other one, to the other side between HQ and branch A, very similar information. Actually, yeah, this one has a little bit more, but here packet 18 is where I did a reset to have all the messages. Well, actually the reset is before because we're closing that TCP connection. But anyways, let's pay attention to 18 and below. Very similar information. Just pay attention to the time to live. It's set to 5 now. But it's going to go through the same process. First, the 3-win handshake, SYN, SYN ACK, ACK. We're going to start exchanging some open messages coming from both sides. This one from 77 to 11, and this one is from 11 to 77. Some keep alive messages, the update messages, and I can open this one too. And this particular one is saying, hey, the prefix I'm sending to you, in particular, the attributes are IGP, as we saw earlier, but now the path is different, right? We are appending the 77 AS, things like that, right? So that's how it's going to work. How is that the BGP session is going to work? And as you can see, I also captured some OSPF hello packages and SLAs there going to the multicast address there. But that's what I wanted to show you. BGP in a nutshell. Hopefully that was really helpful. Let me know if you have any questions. And I think that's it. Thank you very much.